this lecture we will give the complete algorithm, non-deterministic algorithm to check for primality. Okay. So, the algorithm will have two inputs. The first is the number and the second we will think of it as a list. Okay. So, this list essentially has many components. The first would be the number A and then followed by a prime factorization of n minus 1. So, those we will think of it as P1 comma K1, P2 comma KR. Okay. So, we have a list containing 2R plus 1 integers. So, we can think of this as a regular algorithm where the input is n and L is the certificate. So, from L one can in some sense deduce that n is prime. So, what are the checks that one has to do? So, the first check would be check that A raised to n minus 1 is congruent to 1 mod n. Okay, that is the first check. The second check would be check that A raised to n minus 1 divided by Pi is not congruent to 1 mod n. The third check would be check that n minus 1 is equal to P1 to the K1, P2 to the K2, PR to the power KR. The fourth check would be check that all the Pi's are prime. Okay. So, this fourth check we will not bother about it for the time being, but let us say we first do these 3 checks and then make a recursive call to the same procedure. Okay. So, let us first focus on the first 3. If you look at the first 3 checks, how much time will we take for the first 3 checks? Now, we need to compute A raised to n minus 1. That can be done via repeated multiplication. Okay. So, fast exponentiation would take, let us say, time will be proportional to log n. Okay. Because A raised to n minus 1 can be computed as A square, A raised to 2 raised to j and so on, and then multiply amongst themselves. So, the time taken is going to be something like a polynomial in log n. Okay. Because each terms here can be computed by multiplying it with the previous term. Okay. So, A square into A square gives you A raised to 4 and so on. So, we can compute all these terms by performing at most something like c times log n multiplications. And once all these terms are obtained from the binary representation for n minus 1, we can compute A raised to n minus 1. So, the total time is bounded by some polynomial in log n. Okay. So, I will just write it as polynomial in log n. The second step is again A to the power n minus 1 by Pi. So, n minus 1 by Pi is going to be some number smaller than n minus 1. So, that is also going to be some polynomial in log n. But we might have many such i's, but the maximum number of i's is going to be at most log n. Okay. So, since the number of prime factors are small, this is going to be less than log n. So, number of Pi's is going to be at most log n. Well, the input list could when we just look at L, it could have more than log n numbers, in which case we can just right away say that the check has failed, because any list with more than log n numbers would not really be a proper certificate. Okay. But even if it is less than log n, it could be the case that in each of the individual PIs may not be prime, that we will check later. And we will additionally check the third part, and the third part would take, it is again repeated multiplications, Pi to the Ki. So, it is going to be R multiplications. So, log n multiplications okay, and each of those terms. So, this is one term, another term, and there are Kr terms, and the number of R terms, and the total number of terms is bounded by log n. So, if you compute all these, then you are on good grounds, and each of the individual terms, the Krs are at most n or at most log n, and therefore again the total cost of step 3 is bounded by some polynomial in log n. And once all these are done, we need to now check whether the PIs themselves are prime. We can imagine that each of the PIs is at most half of the original ones. I mean, if the original number was n, each factor is at most half of the original number, and we can just recurse. We can represent this by a tree. At the first stage, we are factorizing n minus 1, and then there are recursive calls. We can unroll the recursion tree and do it in a non-recursive fashion. But at each of these nodes, the cost is at most half of the original one, and the total number of these nodes at any level is at most log n. Okay. So, since each node is no more than half of the original one, the total depth of this is going to be bounded by log n. Okay. So, here is a tree whose depth is bounded by log n, and therefore, you can do the computations and ensure. If you look at all these recursive calls together, that is not going to be a huge tree. So, if all the factors were distinct, you would get at most log n different factors, and each of these factors is at most half of the original one. So, the branching factor is bounded by log n, okay, and the total depth is again bounded by log n. And let us look at any intermediary stage. I mean, the total number of small instances, these prime numbers, they should not multiply out and give something say larger than n minus 1. So, again the width at no stage is greater than log n, and therefore, the total tree bound, the size of the tree is fairly small. Okay. Right now argued is that the total computation is going to be some poly log n. Now, we need to argue that if these conditions have been verified, then the number is indeed prime. Okay, that is one thing. So, to verify, if conditions 1 to 4 are checked, then n is prime, and the second thing is, for every prime there exists a choice of L which results in condition 1 to 4 being true. Okay. So, why is it that any prime number has one such L? That is true from the theorem that we had earlier, which said that for any prime number, if and only if there exists an A such that A raised to n minus 1 is congruent to 1 mod n, and for all the smaller numbers A raised to x will not be equal to 1 mod n. Since such an A is guaranteed, we know we can construct an L which passes these tests. why is it that any A which passes these tests, I mean if you have one such A which passes these tests, then how can we say that the number is prime? Well, so we will assume that the PI's are prime, okay, because of our check 4, and then we will assume that n minus 1 is equal to product over I Pi to the Ki. Okay. These conditions we have checked, okay, and the next condition that we have checked is A raised to n minus I by Pi is not equal to 1 mod n, and we know that A raised to n minus 1 is congruent to 1 mod n. Okay. What we need additionally is A raised to x is not equal to 1 mod n for all x less than n. Okay. How do we show this? Well, suppose there is one such x, such that A raised to x is congruent to 1 mod n. We can look at dividing n minus 1 by x. So, C x plus d is equal to n minus 1, okay, and if d is 0, then what we have is A raised to C x is equal to 1 mod n, and C x divides n minus 1. If you look at n minus 1, n minus 1 has all these factors, n minus 1 by p 1, n minus 1 by p 2, n minus 1 by p 3, n minus 1 by p k. So, if p 1 to p k were the factors of n minus 1, then these are the largest factors of n minus 1. Largest in the sense, if you look at the Hasse diagram of these factors, then these are in some sense the largest. Okay. Every other factor of n minus 1 will have to divide one of these. Okay. So, we can write that every factor, we will write every other factor of n minus 1 divides one among the n minus 1 by pi's. So, suppose you have a factor, let us say alpha into k is equal to n minus 1. So, alpha is equal to n minus 1 by k, okay, and we have looked at all k's which are primes, and therefore, this is going to be a smaller number. Okay. So, we can conclude that one of these, I mean if you have alpha equals n minus 1 by k, n minus 1 by k divides n minus 1 by for some pi. Okay. Since we have this condition, we can conclude that if a to the power cx is equal to 1, then a to the power n minus 1 by pi is equal to 1 mod n for some I. Okay. So, that would contradict what we have already checked, and therefore, d cannot be equal to 0. If d is not equal to 0, then d is smaller than x. Okay. In that case, if we had started off this particular assumption by assuming that x is the smallest such integer, then d less than x would contradict our assumption. Okay. So, we can say that this is contradicted by the assumption that x is the smallest such. Okay. So, if it passes these 4 tests, then it is certainly prime, and for any prime number there is a choice of L which will result in these 4 tests resulting in the value true. Okay. So, we will stop here and look at randomized algorithms for checking primality. Now, what we have seen is a non-deterministic algorithm. We will see that there is a randomized algorithm as well for checking primality.